Hello, my name is Shin Aoki from Faculty of Pharmaceutical Sciences, Tokyo University of Science, Japan. I appreciate the organizing committee of ICMSN 2021 for giving us this great opportunity. Today, I'd like to talk about some recent result on the combinatorial synthesis of metallosupramolecular phosphatases formed by the self-assembly of functionalized building blocks. Before I start my presentation, I'd like to talk about the phosphorylation and dephosphorylation of peptides in living systems. These reactions, phosphorylation and dephosphorylation, are important reactions in living cells. And one example is the phosphorylation of tyrosine protein to give phosphorylated tyrosine, which activates the signaling pathways of many intercellular events such as cancer or whatsoever. Therefore, the inhibitors of kinase has been known as the molecular target drugs or anti-cancer agent. And our interest includes the hydrolysis phosphate to regenerate the phosphate-free peptides, which is carried out by phosphatases in living systems. One of our important research project is design and synthesis of artificial phosphatases to hydrolyze this one to phosphate-free proteins or peptides. The promoters have been reported by these several groups for the hydrolysis of the phosphate monoesters, and these groups reported di-cobalt, di-zinc, and di-copper complexes, and these di-metal complexes work, but no compound were reported to function as the catalyst for the hydrolysis of phosphate for AMP and AMP. Several years ago, we have found that di-zinc complex having BPY unit and barbital copper assembles in 2:2:2:2 ratio in extrusion and neutral pH to give supramolecular complex as shown here. This supramolecular complex is formed by the coordination bond between the protein nitrogen to zinc here, and the two BPY units accommodate two copper ions, copper cation, then the two hydroxide anion bridges to these two copper ions. We have found that this molecule accelerates the hydrolysis mono,4-nitrophenyl phosphate, which is abbreviated as NNP, in aqueous solution and neutral pH to give 4-nitrophenol and inorganic phosphate. The structure of SUP222 complex was confirmed by X-ray crystal structure analysis, in which you can see the di-zinc complex here, two barbital unit, and mu complex including two copper and two hydroxide anions. We checked the formation of these supramolecular complexes by many analytic methodology and found that two barbital unit, two zinc complex assembles to form 2:2:2 complex at the neutral pH, and then two coppers are accommodated between two PPY units like this one to resulting in the formation of 2:2:2:2 complex of zinc complex and barbital and copper. This slide shows the crystal analysis of supramolecular complex in top view, side views, and diagonal view. Once again, you can see the copper, two coppers, four-member ring, including two coppers, two hydroxide anion in the center of this molecule. Then we carried out the hydrolysis of the phosphate NMP in the presence of this supermolecular complex in aqueous solution at neutral pH. If this reaction works, the product will be 4-nitrophenol and inorganic phosphate, and this reaction can be followed by UV absorption at 400 nanometer, corresponding to the formation of 4-nitrophenol. Then, after incubation for a long time, we could observe the increasing increase in the absorption at 400 nanometer yellow color, and this change was plotted against the reaction time, and in the presence of one equivalent of supercritical complexes, the hydrolysis proceeded about 40%. For comparison, the no-catalyst diazine complex and kappa BPY complex negligibly accelerated the NP hydrolysis, and in the presence of 0.2 equivalent of both supercritical complexes, the hydrolysis NP proceeded in about 5%. That means this supercritical complex is accelerated the hydrolysis of NP, but not catalytic. This is the reason. This reason could be the product infusion by inorganic phosphate, which is a product of the NP hydrolysis. But anyway, we have succeeded in the formation of hydrophilic supercritical complexes by mixing diazine complex, pyruvate, and copper. Next, we decided to design synthesize the hydrophobic supercritical complex by introducing the hydrophobic long alkyl chain here, which may resemble the mechanical monster in the movie Matrix. The reason why we design synthesize is presented in this slide. This is the schematic model of natural enzyme alkaline phosphatase that has the hydrophobic active site in aqueous solution. The substrate NMP is extracted from aqueous solution to active site. Then the undergoes hydrolysis, and the product NP 4-nitrophenol and inorganic phosphate will be released to aqueous solution to regenerate active site of the AP alkaline phosphatase. We hypothesized that this situation could be mimicked by using two-phase solvent system, aqueous solution and organic solvent systems. The organic solvent in the hydrophobic at the catalytic site could extract the substrate from aqueous solution to organic phase and activate, and they promote the hydrolysis and release the products into the aqueous solution to regenerate this active site of the supercritical complexes. Therefore, originally we obtained these supercritical complexes that work in aqueous solution. But next, we decided to use two-phase systems to mimic the mechanism of natural enzymes. This is the reason why we have designed and synthesized the hydrophobic supermolecular complexes by introducing these long alkyl chains. We carried out the NMP hydrolysis in two-phase systems, including chloroform and aqueous solution in 2:8 ratio in the presence of hydrophobic supermolecular complexes. Then reaction proceeds, but yield was less than 20%, suggesting that there was no catalytic activity. But one of our interesting findings was that the reaction obeys Michaelis-Menten Kinetics. This was as proven by the line-Weaver-Buck plot, in which the straight line here were observed. This is very good findings for us, because artificial systems in two-phase solvent system could be good mimic of natural enzymes in aqueous solution. We could determine the Michaelis constants for each supercritical complexes, as shown here. But no catalytic reaction was observed. Therefore, we have designed the amphiphilic supercritical complex by reducing the number of hydrophilic part from 4 to 2 alkyl sites. We assumed that for this compact amphiphilic supermolecular complex could be located at interface between aqueous solution and organic solutions for the more efficient extraction of NMP to this active site. Then after release of the products, this reaction site could be regenerated to activate next substrate. Then we carried out the NP hydrolysis in the presence of amphiphilic supramolecular complexes in two-phase solvent systems, and found that this one react as the catalyst because only 20% supramolecular complexes gave the over 20% chemical read in this NP hydrolysis. Therefore, we succeeded in the design synthesis of the catalytic supramolecular complex for NP hydrolysis. Then we combine hydrophobic amphiphilic zinc complex with barbital and functional barbital compounds for the formation of supramolecular complex like this one or this one or this one. The next, we focused on the metal ions at the cross position of the active site of alkaline phosphatase. In AP, alkaline phosphatase, magnesium is here to activate the substrate or the protein serine for the hydrolysis of NMP. Therefore, we decided to introduce rich acid at the cross position of the active site of the supramolecular complexes. For this purpose, we decided to use the potassium crown ether unit on barbital unit. The crown ether unit was introduced on barbital unit, which is it was hypothesized that this unit could be located at the cross position of this two mu complex part. Then crown ether part would extract the potassium or other alkali metals from aqueous solution to organic phase to form potassium or other alkali metal crown ether complexes for the activation of substrate. Then we synthesize the crown ether functional barbital and mix with zinc complex in the presence of these alkali metals and confirm the formation of 2,2 complex. And after additional copper, the 2,2,2 complex formation of 2,2,2 complex was confirmed by UV titration experiment. And we carried out the NMP hydrolysis in the presence of this supramolecular complex and found that this one also obeys Michaelis-Menten Kinetics, as shown here, and the potassium compound had the best, highest activity among these lithium, sodium, rubidium, magnesium, lanthanum complexes. Besides, the CTN, catalytic turnover, was checked, and it was found that potassium complex had the highest CTN, catalytic turnover number, among these supramolecular complexes. The Michaelis kinetic parameters of these supramolecular complexes were determined as shown in this table. And this one, AP22, is hydrophilic supracomplexes, 25A is the hydrophobic, and 28A is the amphiphilic supramolecular complexes, and 48A, B, C, D, A, B, C, E is the supramolecular complexes having crown ether, lithium, which is complex with lithium, sodium, potassium, magnesium. And we have found that potassium compound 48B has highest CTN, potassium complex has highest CPN 47 among these compounds, and Ki value is not Km value is not so bad. Kcat value is not so bad again. Although these parameters are not so comparable to these parameters of natural enzyme alkaline phosphatase. Therefore, our next purpose is to improve these parameters to mimic the alkaline phosphatase. This work was introduced, published in European Journal of Inorganic Chemistry this year, and chosen as the front cover articles in volume 13 in this year. If you are interested in our work, please refer to this paper. Then finally, we have succeeded in the formation of this various supramolecular complexes by the combination of these molecular unit A and unit B and couple. Then once again, we synthesize three components as the unit A and many bilateral units as the unit B, and the combination of unit A and unit B gave many types of supramolecular complexes, and we succeeded in finding the best compounds among these supramolecular complexes, which is potassium complex. And we think that this is a very interesting and useful methodology for the screening and finding of the efficient promoters of the catalyst of your target reactions. Finally, I'd like to show you a picture of my research group, and I am proud of working these excellent students and staffs, and I also appreciate these financial supports from these Japanese government and private foundations in Japan. And finally, thank you for your attention. Thank you.